We began class today by you guys looking at the toothpick pattern on page 91, and you had to find how the figure number related to the shape of each figure, and you did a great job with that. And then we looked at the ways that Yolanda and Suki described the nth figure and the total numbers of toothpicks in it to see if they were saying the same thing, and which led us to equivalence. And what that word means is when two things might look different but they really have the same value, they are really equal to each other. And it's pretty important because there's more than one way to solve a problem, and there's more than one way to see a pattern. And when you express it different ways, you need to figure out if they really are saying the same thing or not. So we started with one method, and one method is to use the numbers to test for equivalence. So you simply choose a value for n. For example, if n was 5, we could use Yolanda and Suki's algebraic expression, put in 5 for n, and just simplify to see if we get the same value. So that's what we did. So here was Yolanda's, here was Suki's, so we just took out n and put a 5, and then we use order of operations to simplify. And with Yolanda's method, we got 60, and with Suki's method, we got 60. A second method is to use the tables in your graphics calculator. So we went to y equals, and you entered Yolanda's pattern for the number of toothpicks, and you entered Suki's pattern. And then we went to second function and set your tables. Second function table set is above the windows, and we told the table to begin at 1 and to have increments of 1. That means to count by ones. Okay, and then the next thing we did is we looked at your graphics calculator, and what the table showed is that for each value of x, when x was 1 or 2 or 3 or 4 or 5 or 6 or 7, we got the same answer in y1 and y2, which meant that these two algebraic expressions are equivalent. Okay, and then we took those same two equations, and we just set our windows. We wanted to make sure that everything for x showed, so we went from -1 to 10 for our x minimum and x maxima and counted by ones. And the y-axis, we looked in your tables, and we went from 4 to 112, so we wanted to show all the values from 0 to 120 to be a little smaller and a little bigger. And then we just hit graph, and what you saw was one graph for both of these equations. We had one graph, which meant that one was on top of the other because they were exactly the same. The best method of all is to use properties to test for equivalence. So you have to expand. So leave your 4n and distribute 2n to each term. So 2n times n, which is 2n squared, and 2n times -1, which is -2n. And then we combine our like terms. And then for this one, we want to simplify first. So this is 2n plus 2. And then n times 2n is 2n squared, and n times 2 is plus 2n. So you want to first of all distribute, okay, on this one, and then combine like terms. On this one, simplify first in the brackets and then multiply. And when we did that, we found that n times 2n plus 2, this is Suki's, gives us 2n squared plus 2n. And the first method, Yolanda's, when we distributed first, we had 2n minus 2n, and 4 and a -2n is a positive 2n, so we just bring down our 2n squared and we combine these like terms. 4n minus 2n is 2n, and this is exactly what we got in class in our table. It was in orange for how do we get from the figure number to the total number of toothpicks. And remember, Sarah Neeg said when the gap keeps changing and getting bigger and bigger, we know that there's something going on with squaring. So that's what that pattern showed us. Okay, then you tried it in class, and your first method was to use numbers to test for equivalence, and you guys chose n equals 5 again, and Alyssa chose n is 2. And what she found is for when n was 2, she got 34 for each one of these expressions, and when n was 5, we got 130 for each of the expressions. So we simply took out x and put in 5, and then use order of operations to simplify, and the same with the other expression. So we do know they're equivalent. Okay, and then we used, again, your graphics calculator. You put this in y1 and put this in y2, set our window, and we had one graph, again, to show, or rather in the tables, for every value of 1 through 7, y1 and y2 had the same answer. And then we graphed them. We made sure our window was still set, and we had one graph because one was on top of the other. And then we use properties to test for equivalence, and this shows that it works for all numbers. So once we distributed 3x times x and 3x times 2 and then combine our like terms, for the first one we had 3x squared plus 11x, And the second one, 3x times x is 3x squared. X times a negative 1 is negative 1x. Plus 12x, combine our like terms, and again we get the same thing, 3x squared plus 11x. So they are equivalent. So you have a little bit of homework practice to do, page 95, 2 through 6. Just make sure you show me which method you used, and then get going on ALEKS. So I'd like you to have another hour of ALEKS finished by class on Thursday. And that's it.